Good? All right. So, Chapter 3. So last week we covered Chapter 2 in its entirety, and then on Sunday the Chapter 2 homework quiz and the discussion for Chapter 2 were due by midnight on Sunday. So your next assignment is going to be due this coming Sunday, and it's going to be on the Chapter 3 information. So you have the Chapter 3 homework quiz and then the Chapter 3 discussion, so you're kind of seeing a trend here. When we get into Chapter 4, that chapter is a little bit longer, so it's going to take us most likely more than 1 week to get through. So you'll probably have multiple assignments for that one. So, starting with Chapter 3. So Chapter 3 is all about Newton. So if you notice from Chapter 2, we kind of focused on Galileo and his principles, gravity, all that good stuff. Now with Newton, we're going to start by looking at his 3 laws of motion. So the first law is also known as the law of inertia, and this is an object at rest tends to stay at rest, an object in motion tends to stay in motion, unless acted upon by an outside force. So we're talking all about force, okay? Inertia being, so the reason it's called the law of inertia is because an object's inertia is its resistance to change. Okay, so every object, anything that has mass and occupies space, has a certain amount of inertia. These markers have a certain amount of inertia. They're resisting change. All right. An example I think that I used on the PowerPoints was a soccer ball. So a soccer ball, if it's in motion, it's going to stay in motion unless something stops it. Whether it is the friction of the grass that's going to eventually slow it down, or whether it is a net or another player that simply puts their foot on that ball. Okay, so this is the first law of motion. The second law basically just gives us the equations we need to solve for force. So the second law says force is equal to mass times acceleration. So you need to take into account both mass and acceleration to calculate force. So bringing it back to the soccer ball has a certain amount of mass. So if you know its mass and you know at the rate at which it is accelerating, you can calculate the force of that soccer ball. We're also going to look at net force. So what net force is it's the addition of several forces. So force is a vector quantity, meaning it has a magnitude and it has a direction. So since it's a vector quantity, we can figure out the net force by adding separate force vectors together. And we're going to take a look at that not only today in class, we're going to do an example calculating net force, but in lab. So when you do lab 9, which is posted in the lab folders right now, and we're not doing it for I think another week or 2, but you could do it now since we're talking about force. You're going to be using this equation a lot in that lab to calculate force, because for the force vector lab, you're actually doing a lab simulation where you have people with a tug on a rope playing tug of war with the rope, and you're going to be calculating the net force based off of their force vectors. The third law of motion, so the last one. For every action, there is an equal and opposite reaction. So I recommend you watch the PowerPoints to see some examples of that. It just means for every force applied, there's an equal and opposite force applied back. Okay, so even me just putting my hand and leaning on this wall, I'm applying a force to the wall, but the reason I'm not falling through the wall is because it is also applying an equal and opposite force back onto me, allowing me to stay upright and lean on it. Okay. So, with these laws of motion in mind, let's look at some problems and put the equations to use. So there should be an equation sheet posted in Blackboard under the, what week are we in, week 5? Week 5 folder. And this is going to have the force equations that we're going to be using. So it has Chapter 3 equations, and then it also has the equations for the next chapter. So it is two-sided. So you can see for the Chapter 4 equation, there's much more equations, so that's why that chapter takes a little bit longer to go through. What we're looking at on the board, calculating problem-wise, we're looking at the problems from the PowerPoints. So as you go through the PowerPoints and learn about the concepts, every now and then there'll be a slide with some questions on it, and that's what we're covering during class periods here. So for the first problem, we're looking at a tug-of-war scenario, and this is similar to what you're going to see in your lab, so the force vector lab, there's going to be a lot of problems just like this. So we have two people applying a 125 Newton force to the right. Direction is important because force is a vector, so we need to know the direction and the magnitude. Then on the other side of the rope, we're going to have only one person, and they're applying 110 Newton force to the left. So what we're going to figure out, who wins? Who wins the tug of war, and what is the net force? So it might be easier to figure this out if we had a visual. Right? So let's draw. I'm going to have my tug of war. Here's my rope. Here's the middle of it. The point in which we figure out who wins, we have two people pulling it to the right. So the two people would be over here, and I'm not an artist, so I'm drawing stick people. So we have two people on this side of the rope, and they're pulling it to the right with 125 Newton force. Notice, units on force are in newtons. Why? Because Newton came up with the laws of motion and the force equation itself. Okay, so we measure force, F is equal to newtons. On the other side of the rope, we have one person, it says, and he's applying a force to the left, so I have the arrow, at 110 newtons. So just by looking at the numbers themselves and comparing them, who do you think is going to win? Well, it's going to be the ones that are applying more force. So it's going to be the people that are pulling to the right that are going to win. But we need to also be able to calculate, okay, but how much are they winning by? What is the net force? So in this case, since they are pulling different directions, that means one of these forces is positive and the other force is negative. So when we're calculating net force, we have this equation here to calculate net force. We're actually subtracting these from each other because they're opposite directions. If they were applying the forces in the same direction, we would add them. But since they're pulling them in opposite directions, we're actually going to take 125 and subtract it from 110 to get our total net force. So our net force is going to be 15, and the units on it are going to be newtons, because we're still talking about a force, so it's still newtons. But since it's a force, we want to also pull a direction. So subtracting them, that means the people on the right are going to win because they are applying 15 more newtons of force than the person on the left. So the people on the right are going to win. So what direction is the rope going to go? To the right. So 15 newtons to the right is the sum of forces, or the total net force. So the key for problems like this is knowing whether they are applying those forces in the same direction or opposite directions. If it's the same direction, we add them together. If it's opposite, we subtract them. All right. So let's look at another problem. So that is a net force problem. Now let's look at using that F equals ma. Let's try to apply that. So number 2, the PowerPoints, we have a 3.9 kilogram boulder. It's accelerating north at 1.7 meters per second squared, and we're going to calculate the resulting force causing this acceleration. So if you want the full wordage on that question, you can look at the PowerPoints for it, for the virtual people. So I'm going to approach this like I did my philosophy problems. I'm going to label the numbers in the problem itself with variables, and then I'm going to pick an equation and go from there. So starting, this 3.9 kilograms, I need to know what that is. Well, kilograms, the units tell me, they say that that's a mass, so I'm going to label that with an M. This is my knowns and unknowns portion, if you recall from the velocity equations. So the other piece of information, the 1.7 meters per second squared. To figure out what that is, you can either look at the wording, which tells you the boulder is accelerating, so this would be my A. But the units also can tell you that, because meters per second squared, that's what we measure acceleration in. For the unknown, it asks us to calculate the resulting force. So we're calculating F. So this is the easiest type of force problem that you'll see, because you don't have to rearrange the equation or anything. We're going to be using the equation F equals ma that we get from Newton's second law, and we're just going to plug in the two pieces of information. Now notice the mass is in kilograms. That's what we want it in. If it was in grams, then I would need to convert it to kilograms before I plug it into the equation. So I have 3.9 for my mass, and I'm going to multiply that by 1.7, my acceleration. When I do that, notice I'm going to only have two significant figures, so we don't want to forget about significant figures yet. So my calculator spits out 6.63, but that's three significant figures. So I'm just going to report the first two. So 6.6 is my answer, but I always want units as well. So when I'm calculating force, we said the units on force were newtons after Sir Isaac Newton. So pretty straightforward. Let's look at a more complicated one now. So the next one, we have an 1825 Newton force is used to move a car with a mass of 1550 kilograms from rest for 22 seconds. And we're going to calculate all kinds of things. So we're going to calculate, it asks for acceleration, velocity, and distance. So our next exam is going to be on chapters 2, 3, and 4. They're all going to be together. Why? Because they go together. Notice we're going to calculate acceleration, but it also asks for velocity and distance. So we're going to be using some equations from the last chapter to calculate those two. So we're all combined. So before I go looking for equations, let's write my list of knowns and unknowns. So, my first piece of information, 1825, that's a force. I know that because it's in newtons. That's what we measure force in. My second piece of information, the 1550 kilograms, that's a mass. And it says that specifically in the problem. The car has a mass of 1550 kilograms. I'm also given a time of 22 seconds. And unknowns are acceleration, so A, velocity, V, and distance, D. Three unknowns, that means I'm going to be using three different equations. Okay? Since this is the force chapter, you can guess that we're going to use the force equation, F equals ma somehow. And we are. We're going to use it to solve, in this case, for the acceleration, for the A. We have the force, and we were given the mass. So we're going to rearrange that equation to solve for A. And remember, when we're rearranging equations, we do the opposite operation. So right now we're taking mass and multiplying it by acceleration. So to get rid of the m, to get it on the other side of the equation, we're going to divide by m. That way, they're on opposite sides of this horizontal line and they cancel. Whatever I do to one side of the equation, I have to do to the other. So to solve, I'm going to take my force and I'm going to divide it by my mass. So 1825 divided by mass 1550. And in this case, 3 sig figs, because the two numbers I used, one has 4 sig figs, the other has 3. I picked the smallest. So 1825 divided by 1550. And I said 3 sig figs, so it's going to be 1.18. And since it's acceleration, my units on acceleration are meters per second squared. So that force being applied to that car to try to get it moving, it's going to accelerate at 1.18 meters per second squared. This is why acceleration and mass are inversely proportional. The higher the mass, the lower the acceleration. It goes up, the other goes down. All right, so we have one piece of information. We still have 2 more to solve for. Now these other 2, velocity and distance, these are going to be in the last chapter. So when I'm looking at the last chapter, the equations I'm going to focus on are going to be the 0 initial velocity equations. Why? Because of this key piece of information here. It says the car was at rest. It was originally stopped, not moving. So its initial velocity is 0. Okay, so we're using our 0 initial velocity equations. And we have this guy to solve for velocity. We have 2 distance equations. One of the distance equations has average velocity in it. We're not going to use that one because we don't have average velocity. The other distance equation is that 1/2 AT squared. Those equations work with no rearrangements to them, so that's why I chose them. We have acceleration, and we also have time, so I just plug that in. So a little review from last chapter. So for the velocity, I'm going to take my 1.18, my acceleration, multiply it by the time. They moved this vehicle for 22 seconds. For distance, same thing, 1/2. I'm going to put my acceleration, and my time is going to be squared. So let's figure out how far did they move the vehicle, and what was the velocity of the vehicle. 22. So it was going, how many sig figs? 2 sig figs for this one, because the time was given in 2 sig figs. So we want our answer in 2. So it's going to be 26, we have to round up, meters per second. I had it moving pretty fast. Now let's do the distance. And it moved quite a distance as well. So 22 squared times 1.18 times 1/2. Again, and we want just 2 sig figs again. So let me show you how this one works. This one's kind of a strange one for 2 sig figs. So this is what my calculator spits out. Okay, but I just said 2 sig figs. So remember, we go from left to right. So the 2 and the 8 count. Look to the number next to it. Since it's a 5 or higher, that 8's going to round up to a 9. And where the 5 is, I'm going to put a 0 because I need a placeholder there. I need it to stay in the 200 range. So 290, in this case meters, would be your answer. Once again, that time that we used had 2 sig figs, so we need 2 sig figs in our answer. Now on the homework, this would have been 3 separate questions, right? Because I only ever asked you to solve for one variable for each question. So it was a little intensive, but it would have been multiple questions. All right, let's try another one. The next one, where you have a 1944 kilogram Challenger, so a Challenger being a type of car, and it's accelerating from 0 to 60. Miles per hour in 2.3 seconds. We're going to calculate how much force is required to achieve this. All right. Well, space in this little section, so I'm going to erase this guy over here. So we're basically saying you have a Challenger. Challenger vehicle boasts that it can go from 0 to 60 in 2.3 seconds. So we're going to calculate how much force is required to actually make that statement true. So this is going to be a long one for several reasons. One is, when I write my knowns and unknowns, I'm going to notice something. So let's just start with the first number, the kilograms. Kilograms is in mass. I'm going to label that with an M. My next piece of information is 60 miles per hour. What is miles per hour? It's a speed, a velocity. But notice the units itself. We can't use miles per hour with the equations that we have. We need metric system. Okay, so this needs to be converted to meters per second. So there's a little extra step there before we use the equations. Last piece of information, time. 2.3 seconds. That's in the units we want, so we leave him alone. The unknown is going to be the force, so I'm going to put F with a question mark. So before I pick equations, I just said I'm going to convert. So that's what I'm going to do over here. I'm going to convert 60 miles per hour to meters per second. In order to do that, I need a conversion factor. So from last chapter, I gave you a conversion factor where you had 1 mile per hour equal 2.447 meters per second. So when we do conversions, so this is like all the way back in chapter 1, you start with the number you're trying to convert. So I'm trying to convert 60 miles per hour. That's what's going to start your plus sign, your railroad tracks, your dimensional analysis. Then you're going to take the conversion factor and you're going to put it here. And figure out what goes on top, what goes on bottom. You're trying to cancel out what you don't want. So we're trying to get rid of miles per hour, so I'm going to put the 1 mph on the bottom. On the top, I'm going to put the 0.447, because that's the meters per second. That's what I want. So what is 60 miles per hour in meters per second? To figure that out, I multiply across, so 60 times 0.447, and I get 26.82. Notice I'm not worrying about sig figs here. Why would I ever not worry about sig figs? Because this isn't a final answer. Okay, I want to keep all the digits I can until I get to the final answer, just to get a more accurate answer. So that's why I have 4 instead of rounding it to 3. Now, I have the units that I need. So next, I can figure out what equations to use. Now, if I'm calculating force, the only equation we've talked about so far for force is mass times acceleration. So I know I'm going to have to use that. But I have mass, but I don't have acceleration. So that's what this extra information given to us is. It's going to help us solve for the acceleration. So I need to calculate acceleration first. What type of equations am I going to look at? Well, this car went from 0 to 60. So it started at rest. 0 initial velocity equations is where I'm looking. And when I look at the 0 initial velocity equations, the first one I'm going to look at is the one where a is equal to, and see if that one works. So under the 0 initial velocity equations, I have a is equal to v over t. Okay, does that one work? Well, let's see. I have velocity, and I have time. So yes, I can use it. When I use it, I need to make sure I'm using the meter per second version, not the miles per hour version. So my velocity, 26.82, goes on top. The time, 2.3 seconds, goes on bottom. So calculating that out, I will figure out the acceleration of that vehicle. And this time, since this is an answer, or this isn't an answer, this isn't an answer, this isn't my final answer, so I'm not going to worry about sig figs again. So 11.66, so I'm just going to keep as many as I can, because this acceleration here is going to be plugged in to that equation. Okay, so the more digits I keep, the more accurate my final answer will be. So only worry about sig figs for the answer you're reporting, not for these in-between steps that we're doing. All right, so my A I now have. The M was given to me in the problem itself. So I'm going to go up here and plug those in. The mass of the vehicle, 1944 kilograms. The acceleration, plug that in, so times 11.66. I get, erase this so I can put the answer right underneath from the room here. 22,668.73 and a whole bunch of other numbers. So I'm going to write all those numbers down because I want to look at the significant figures. How many sig figs am I worrying about? Okay, well, for the force equation, we have 4 sig figs in the mass. We said the sig figs aren't going to matter for the acceleration, so we're just looking at the 4 sig figs in the mass. So that means we want 4 in our answer. It's another one of those weird ones. So let's look at 1, 2, 3, 4. So we want to stop at the 6. Look at the number next to it. It's 5 or higher, so that's going to round up to a 7. So we get 2, 2, 6, 7. But we need a placeholder for that 8. So we're going to put a 0 there. So it's 22,670. What are the units? Force measured in newtons. So for significant figures, I mean, you usually have multiple choice questions, and so the sig figs are done for you. The reason that I'm still going over this in such great detail with the significant figures is because in lab, you need to take into account sig figs too when you're doing problems and questions. So I want you to keep up with the practice. Because you don't get multiple choice in lab. In lab, you have to write it out. So make sure that you are doing sig figs. Make sure you are labeling. So make sure you're putting your units. So if units aren't there, you'll get points docked off as well. All right, try that here. Make sure I don't go over. So we have time for another one. So let's see what's next. So the next problem is a 72 kilogram body is being dragged across a room with a force of 33 newtons. Calculate the change in acceleration if the force is increased to 48. All right, so it sounds like we have a dead body situation in this problem. We have someone's dragging a body across the floor. So they gave us the mass of the body. They told us that they're applying a force of 33 newtons. Well, the problem goes on further to say, okay, they increased their force. So they decided they weren't going fast enough. So they increased their force then to 48, trying to get that body out of there quicker. So what we're going to calculate, what they are asking us to calculate, is the change in acceleration. So let's write our knowns and unknowns. Let's organize this information. The body, 72 kilograms, that's our mass. The force is 33 newtons. Now I'm going to call this F1. The reason I'm calling it F1 is because I have 2 forces, and so I want to keep track of them. So my initial force, I'm going to have F1, Then we increase the force, so my F2 will be 48 newtons. It's asking us to calculate the acceleration. Since I have two forces, I'm going to have two accelerations. So A1 is going to be the acceleration at the 33 Newton force. A2 is going to be the acceleration at the 48 Newton force. Now the mass, this m, I'm going to use to calculate both. Why? Because the mass isn't changing. It's still the same body, no matter what force was applied to it. All right, so let's look at the equation. And so far, we only have one equation for force, and that is mass times acceleration. So I'm going to have to rearrange this equation to solve for A. And we've done that already in a previous problem. To do that, we divided both sides by m, so that we get F force divided by mass will equal my acceleration. So let's apply this. So I'm going to do A1 first. So for A1, the force I want to use is 33 newtons, force 1. The mass I'm going to use is 72, because it's the body that I'm applying force to. A2, it's going to be the same equation, but my force is different. So I have a 48 Newton force for my second acceleration, but it's the same body, so my mass is still going to be 72. Notice two sig figs for both of these. So the top one, acceleration at the 33 Newton force is 0.46 meters per second squared. It's the rate at which they're pulling the body. Then when they increase their force, you can guess, if you're increasing your force, the acceleration should go up too, because they're proportional. Force and acceleration are proportional. So when you increase your force, you do indeed increase your acceleration. It went from 0.46 meters per second squared up to 0.67 meters per second squared. So how do you think you calculate the change in acceleration? You would subtract those two numbers, right? I want to see the difference. When you say the word difference in math, that means subtract. So my change in acceleration, or delta A, that triangle means change, would be my A2 minus my A1. So you always want to take final minus initial. And A2 was my final acceleration. So you get 0.67 minus 0.46. So the change was 0.21. That's the difference. So by increasing their force, 33 to 48, they increase their acceleration by 0.21. I want to do one more problem. And this is the weight of a person. So the next one is, what is the weight of a 12.7 kilogram bicycle on Earth? And how does the weight change if we took that bike onto the moon? So now we're looking at weight. Now weight is actually a force. So don't be confused by seeing the word weight. We're still calculating force. The reason you weigh what you do is because the rate of gravity is affecting your mass. What I mean by that, this is the equation that we use to solve for weight in physics. Because in physics, what weight is it's your mass multiplied by gravity. So it's a force. So whenever you see calculate weight, what you're calculating is F of g, the force of gravity. So in this particular problem, we have 12.7 kilogram bicycle. And we want to know the weight, or the F of g, on Earth, and the weight, or F of g, on the moon. These values are going to be different. Why? Because gravity changes when you go to the moon. So let's look at the information we have. So my knowns and unknowns. That 12.7 kilograms, that's my mass. And that's what I want mass in, so I don't need to convert. But now, it doesn't give us any other information. But the fact that it's asking for you to calculate the weight, we know that gravity is going to factor in here. It's kind of like with free fall problems. When we read the free fall problems, knowing that it was a free fall problem told us, oh, gravity is one of our knowns. Same with weight. When you see the word weight, you're like, oh, gravity is going to be one of my knowns. So gravity on Earth is 9.8 meters per second squared. We saw that from the last chapter. What is gravity on the moon? It is actually 1/6 of the gravity on Earth. So I think that totals out to be 1.6 meters per second squared. So to calculate, we have two unknowns. I have them up here. Let's do Earth first. We're going to take f of g on Earth. We're going to take the mass of the bike and multiply it by the gravity on Earth, 9.8. For the weight, or f of g on the moon, we're taking the same mass, because mass doesn't change just because you go somewhere new. The mass is going to remain constant. You're still made up of the same material. Parts of you don't fall off when you go from one place to the next. What does change is the gravity, and that's going to be 1.6 on the moon. So multiply those numbers out. 12.7 times 1.8. We get 124. 1.6. Oops. If you see any mistakes, please point out, because you enter things in the calculator wrong from time to time. So try to go fast. So those are the values, but values mean nothing without units, so don't forget to put units. So we're talking about weight. I said weight was a force. Force is measured in newtons, just like linear force we were looking at earlier. So it doesn't matter what type of force. We'll see on Wednesday, we're going to be doing centripetal force problems, gravitational force problems, and they're all going to be measured in newtons. So the units will be the same, it's just how we calculate them, the equations that we use are going to differ. So we'll add on to this on Wednesday with centripetal force and gravitational force. So we'll look at the rest of the equations on here. And now that I've looked at the equations on here, I realize that I labeled this wrong, so I'm glad I looked at that. This is not F of G, gravitational force. This is F of W for weight force. So please make that correction. This is why I need more people to come to class, so someone notices and tells me that before I finish the whole problem. So F of W is what we just calculated, weight force, weight force. All right, so we'll look at centripetal force and gravitational force next class. Much different equation for F of G. So make sure your knowns and unknowns are labeled properly so you don't make the same mistake I did. Any questions? No?